Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today we are at lecture number 14 of week 7, and today's topic is open basics. This topic we have started in last class, and we will continue this again in this lecture as well. This is section number 10.4 of your book, and we have started the open, and we have seen that open is available in the form of IC having certain number of pins. This is the pin configuration, and this is the symbol of the open, and in which we have two inputs and one output, and have certain supply connections. So in the last class we have seen that the open with a very large gain, which is the differential gain of the amplifier, which is typically very large. Even for 741 op-amp it is about 200,000 of gain, and the op-amps which came later on have improved gain characteristic, and gain is approaching to infinite ideal value. So ideally the open gain is infinite. So we have seen that with a very large gain of the op-amp, if you apply any input signal, any very small input signal, the output gets saturated and gets into the supply levels for very small values of the input. So there we have seen the limitation of on the input side, that if we want that the output doesn't go into saturation, then we have to keep the input signal and magnitude to a very small value, which is in microvolts, and for ideal op-amp it must be close to 0 volts. So it means that this op-amp as is cannot be used as an amplifier. For that, this to use the op-amp in the to use the op-amp as an amplifier and keep the output unsaturated, we have to limit the input signal to a very small value in microvolts range. So as is, this op-amp cannot be used as an amplifier. It means that we cannot apply the signals of millivolts and volts range, because if signal is large, then with this large gain output gets saturated, and we cannot get the input reproduced at the output with the same shape. That is, if I am applying sine wave, I must get a sine wave at the output. Clipping should not be there. The clipping is occurred because of the op-amp goes into saturation. So ultimately what we can do is we have to reduce the gain of the amplifier, and for that we have see that we have to use the op-amp in the feedback, and more specifically we have to use the op-amp in the negative feedback. So negative feedback will reduce the gain of the amplifier, which was initially increased and achieved, and we have op-amps with a very large gain, which becomes problematic for us, and we have to reduce the gain somehow, and for that we are going to do negative feedback in the op-amp. So this is the structure of the op-amp, in which feedback is applied to the op-amp, and this one is the type of negative feedback, because the signal which is fed back to the input side gets subtracted from the input. So if this is negative, and input is subtracted from the feedback signal, and that subtracted difference is applied at the input of the op-amp, then this is a negative feedback amplifier. And if this is positive, feedback signal is fed back in such a way that it is added with the input. This is plus. If this is also plus, then these two are added, and this added signal is applied into the input of the amplifier. Then this it would be the positive feedback. So positive feedback is also used, but it doesn't reduces the gain. It actually enhances the gain of the overall, and it overall enhances the gain of the amplifier. So negative feedback reduces the gain of the amplifier, and positive feedback enhances the gain of the overall circuit or overall amplifier. So at the moment we have to reduce the gain of the amplifier. So rather positive feedback, we have to use the negative feedback. So let me see how the negative feedback works, and what is the working principle of this feedback circuit, and how the gain is reduced with the application of negative feedback. So towards that, now we are going to analyze the circuit and develop the relationship and find out the closed loop gain, which is V out over V in with the feedback connected. So without feedback, the gain is differential gain, and which is very large, and with feedback in action, with feedback connected, what would be the gain of the amplifier? We would compute the output over input ratio. That would be the gain of the overall circuit with feedback connected. So we have seen that V out is equal to AD into VD, where if you see that the output of this open circuit is V out, and input is here it is VD, then the relationship between V out and VD would be simply equal to V out would be equal to AD into VD. And then we compute the relationship of output with V in rather than VD. So V out, our V in would be equal to, we have to find out, however V out over VD would be equal to AD, and this output signal is fed back using this block, and this block has a gain which is beta, and beta is usually less than 1. That is, the output is fed back to the input side with a certain fraction, and a portion of the input is fed back, not the complete output, rather than a fraction, and that fraction is determined by this feedback block, and that is beta, and beta is typically less than or equal to 1. So in the extreme case, if beta is equal to 1, that means the input would be equal to output, as beta is 1. That is gain of the feedback stage. This is the feedback stage, and beta is representing the gain of the feedback circuit, and beta is typically less than or equal to 1. So for beta less than 1, this signal would be less than this signal. It means the output of the feedback signal block is always less than or equal to the input of the block. So so what would be the output of this block? This output is this one, this is the input, and output of this block is equal to beta times the input of this block. The input is V0 coming from this side, this is V0, and output is here. So output is equal to beta into input, which is beta into V0, because V0 is the input of this block. So this beta V0 is the signal which applied here, which is a sub difference block, this circuit or this symbol is used for the difference circuit. This performs the difference of these two inputs and give an output which would be the difference of the inputs. So this is symbolic representation of the difference circuit or different block, and the output of this difference circuit would be subtraction of these two inputs, that is this input minus this input would be equal to VD. So V in minus beta V naught would be equal to VD. So VD would be equal to V in minus beta V naught. And so plugging the value of VD in from this equation into this, so V naught would be equal to AD into V in minus beta V naught, and then multiplying AD with each term inside, then it becomes AD into V in minus beta AD into V naught. So combining the same terms containing V naught here, V naught here, so take this up to the left, so it becomes plus beta AD into V naught, that would be equal to AD into V in. So taking V naught common, so this becomes V naught into 1 plus beta AD, which is equal to AD into V in, and then taking this term to the right, then we get V naught would be equal to AD into V in divided by 1 plus beta AD, and then we can bring this V naught to the left, this would divide here and becomes V naught over V in. V naught would be V naught over V in is called the gain of the amplifier, and this is called the closed loop gain of the amplifier, because now we are computing it with the closed loop connection and feedback connection. So when it is when the op amp is in feedback, then the amplifier gain would be the closed loop gain. If feedback is not present, then the gain of the amplifier is the differential gain, or also called the open loop gain. So no loop, open loop, or no feedback. So closed loop gain of the amplifier would be equal to AD over 1 plus beta AD. So this is the relationship of the closed loop gain that we have arrived in the previous slide, and we want to see that how much this closed loop gain would be for a given a differential gain. So how it depends upon the differential gain of the amplifier. So we are now considering 4 cases in which we are assuming that in each case, for example, in first case differential gain is 100 and beta is 0.1. So then with AD equal to 100 and beta is equal to 0.1, then what would be the closed loop gain? So this AD is this one, and beta is this feedback gain. So beta is assumed as 0.1 and the forward gain or differential gain is 100. Then the closed loop gain would become equal to this is 100 divided by 1 plus beta is 0.1 into 100. So this 100 divided by 0.1 into 100 is 10 plus 1, which is 11. So this number would be equal to 9.09. In the second case, we are considering gain equal to 1000 rather than 100, and the value of beta is still assumed as 0.1. So in each case, beta is assumed 0.1 and gain is increased from 100 then 1000, and then we are assuming gain to a very large value. Then we want to see what is the impact of this gain. If this gain is ideally very large, then what would be the closed loop gain with this very large gain of the amplifier. So as the gain becomes 1000, the closed loop gain becomes equal to 1000 divided by 1 plus 0.1 into 1000. 0.1 into 1000 is 100, and plus 1 is 101 dividing 1000 with 101 becomes equal to 9.9. So closed loop gain is now increased from 9 to 9.9, and then we replace in the third case we consider gain to be 10 raised power 5. It is quite very large as compared to the gain considered in case 1 and case 2. So if gain is 10 raised power differential gain is 10 raised power 5, then closed loop gain will be equal to 10 raised power 5 divided by 1 plus 0.1 into 10 raised power 5. 0.1 into 10 raised power 5 is 10 raised power 4, and plus 1 would be approximately equal to 10 raised power 4. So 10 raised power 4 divided by 10 raised power 5 divided by 10 raised power 4 would be equal to 10, because if this denominator is shifted to the numerator, then power becomes 10 raised power minus 4, and 10 raised power 5 into 10 raised power minus 4 is equal to 10 raised power 5 minus 4, which is 10 raised power 1, so it is 10. So in case number 4, differential gain is even further increased to 10 raised power 10. So with 10 raised power 10 differential gain, plugging this value in the original equation, then I will get 10 raised power 10 divided by 1 plus 0.1 into 10 raised power 10, which is 10 raised power 10. Our 10 raised power approximately 10 raised power 9, which is again 10. So you can see that if my differential gain gets very large from the lower value, and it gets very it increased to a very large value, the closed loop gain approaches the value of 10. So you can see that as long as the differential gain is very large, the closed loop gain is independent of the differential gain, whether it is 10 raised power 5 or 10 raised power 10, it doesn't affect the closed loop gain of the amplifier, it remains constant. So again, starting with this equation that we have derived in slide number 6, this equation can be written as closed loop gain is equal to this AD is bring into the denominator divided here, and this becomes 1 over 1 plus beta AD divided by AD, and if I divide this by the denominator, this becomes 1 over AD plus beta AD over AD, and AD cancel, this becomes beta. And now we are now looking at the case 5, in which gain is now approaching to the infinity, and I am taking gain as infinite, differential gain as infinity, and still beta is 0.1. Then closed loop gain with the AD infinity becomes equal to, if AD is infinity, 1 over infinity becomes 0, and 0 plus beta is beta, so 1 over beta. So closed loop gain becomes 1 over beta, and which is equal to 1 over 0.1, beta is 0.1, which is 1 by 0.1 is 10. So even gain, differential gain or open loop gain becomes infinite, the closed loop gain is still the same, which is equal to 10, and you can see that it only depends upon beta, and whatever the beta is, the closed loop gain of the amplifier is 1 over beta. If beta is 0.1, the closed loop gain is 10. If beta is equal to maybe 0.2, then gain would be equal to 5, and so on. If beta is equal to 1, then closed loop becomes 1. So all that we conclude at this point is the closed loop gain of the amplifier is independent of the open loop gain or differential gain, and it only depends upon the value of beta, and beta is the feedback fraction or feedback gain of the overall feedback amplifier. So we can set the closed loop gain of the amplifier by setting the value of beta. For different gains I can set the different values of beta, and the gain of the amplifier would turn out to be the reciprocal of the beta. So let me apply the same negative feedback action of the amplifier with our op-amp, in which this is the op-amp having two inputs, and in order to use this op-amp in the negative feedback, we have to apply an feedback signal back to the negative terminal of the op-amp. So if the feedback connection is applied to the negative side of the op-amp, then the op-amp would be in the negative feedback, and if the output connection is fed back to towards the positive side of the op-amp would be in positive feedback. So this is the negative feedback action applied to this op-amp, and we want to see how this circuit would work. As we have seen for an op-amp, for a symbolic block diagram, that negative feedback action and derive the relationship of the gain of the amplifier in the feedback scenario, and come up with the closed loop gain of the amplifier. So similarly, we want to see how in the actual circuit, in an actual op-amp, when we apply the feedback to the op-amp, and now what would be the now new gain of the amplifier with the feedback connected. So you can see that in this case two resistors are used to provide a feedback signal to the input side. The feedback block, this feedback block is now represented, and it consists of these two resistors, and when I give a feedback to this block, and then I get an output from this block. That output is taken from this common point, and this feedback signal, that is the divided signal of these two resistors, and is fed back to the input side of the op-amp, and this feedback signal is fed back to the input side of the op-amp. So input minus the feedback signal is the VD of the amplifier. Here input minus the feedback signal is the VD of the amplifier. VD is what? VD is the difference voltage, that is V in 1 minus V in 2, which is the difference signal appeared at the input of the amplifier. This difference signal is amplified by the op-amp and give me the output. So what would be VD here? That I am going to compute it. So VD would be equal to V1. This V1 is the signal at the non-inverting input, and Vf is the signal that is applied at the inverting input. So VD is equal to V1 minus Vf. So this is VD, and we have output would be equal to AD into VD, and VD is equal to V1 minus Vf. So Vout is AD into VD, VD is equal to V1 minus Vf. So Vout is equal to AD into V1 minus Vf. Vf is equal to that you can compute here. What is Vf here? So voltage at this point would be equal to R1 into V0, applied voltage to this series circuit. Applied voltage to this series resistors is V0, and voltage fraction or voltage at this point would be equal to voltage using voltage divider tool, R1 into V0 over R1 plus Rf. We are assuming that the current into this input terminal is 0. That is current when voltage appears here, and that because of this voltage, a current would flow in this circuit, and this current would be such that when this current arrives at this point, no current would divert into this link, and the current coming from this point would follow this resistance, and this current and this current would be equal, and no current entering into the open input terminal, because we are assuming that the input impedance of the amplifier is very large and ideally infinite, so it doesn't take any input current. So voltage at this point would be equal to Vf, which is R1 into V0 over R1 plus R2, and which is equal to beta V0, and where beta is equal to R1 over R1 plus R2. So this resistor ratios is defined as beta. Beta is constant, as the resistors are constant. So if this is the case, then Vf would be equal to beta V0. So from this point we can quickly calculate the ratio of the V0 and V1. V0 and V1 is equal to ACL closed loop gain, which is equal to AD over 1 plus beta AD. So this is the same result that we have arrived for the block diagram of op-amp with negative feedback, and this is the actual circuit of the op-amp, which is non-inverting amplifier with a feedback connection on the negative side. So closed loop gain is this, and if I plug the value of beta in this equation, then I can compute the closed loop gain. So first see, this equation is rearranged in this form, and if AD is infinite, or even AD is very large in 200,000 or above, then this 1 over the AD would be a very small value, and where my closed loop gain would be equal to 1 over beta, and beta is equal to R1 over R1 plus RF, and rearranging this, bringing this on the numerator, then this becomes R1 plus RF over R1, which is equal to 1 plus RF over R1. This is divided by this becomes 1 plus RF over R1. So V out is equal to, as you know, if you have a gain of the amplifier, then output would be equal to gain into the input, and gain is equal to 1 plus RF over R1. So this is the gain of the amplifier, and assume that these two resistors are specified as R1 is 1 kilo ohm and RF is 10 kilo ohm. Then with R1 1 and RF 10k, RF 10k and R1 1k, you can compute the closed loop gain of the amplifier as 1 plus 10, k over 1k is 10, and 10 plus 1 is 11. So closed loop gain of the amplifier of this amplifier would be 11, whereas the open loop gain is infinite. So output is equal to gain into input, and gain is 11 into input. So with this equation, I can find out the output of the amplifier for an input, given input. So for example, given input is a sine wave of value of 1 volt peak, and what would be the output? Output would be equal to 11 into input. So input is 1 volt net peak, then output peak would be equal to 11 into 1, which is 11 volt peak. So you can see that the op-amp with the battery voltages of plus 15 and minus 15, and the output is not hitting the saturation level. Output is still below the saturation level of supply voltage, so output would not be clipped. And for a 1 volt input and a gain of 11, I will get an output of 11 volt peak, and when input is minus 1 volt, output would be equal to minus 11 volt, and I will get a neat sine wave at the output for a sine wave at the input of this amplifier. So this amplifier is now collected in feedback, and the gain of the op-amp is reduced to a very low value using these resistors in the feedback, and choosing the appropriate values of these resistors. I can set the gain of the amplifier to any value of maybe a very low value of maybe 1 volt to maybe 10 of 1 and to any value of maybe 10, 11, 100, 1000 or so. So if I increase, for example, value of RF to 100k and R1 equal to 1k, so if it is 100k and it is 1k, the gain would be equal to 101. So 100 divided by 100 is 100 plus 1, 101. So gain can be set to any value by choosing the values of these external feedback resistors. So this is how you use the op-amp in the negative feedback to achieve a gain, closed loop gain of any desired value, and you can use this op-amp as an amplifier. So that's it for today, students. Thank you very much. We will move on from this point and see other amplifier configurations. Thanks a lot.